Hi, this is Adam Griffin with the first video for this week. So this is going to be problem 3, which deals mostly with torque and system in equilibrium. So we're going to be learning how to relate masses in a system and distances to torque on a point, or about an axis. So number 3 goes like this. So there's a rigid uniform horizontal bar of mass m1 and length L, and it's supported by 2 identical massless strings. The figure shows a bar of length L and mass m1 placed horizontally and supported by 2 vertical strings labeled A and B. The left end of the bar is attached to the top end of the vertical string B, right here, and then which bottom end is fixed to a horizontal surface. So this surface right here. And then we have string A, which is attached d distance from string B, also attached to another surface. So we also have a block of mass 2 that rests on the bar x distance from string B. And the distance x is greater than d, as we can see from this. And then both strings are vertical, so we know that all of these like angles right here are 90 degrees exactly. So it also tells us that d is less than half of the length of this plank, and the block of mass m2 is supported against gravity by the bar at a distance x from the left end of the bar as shown. So we have to express the tension in string A in terms of gravity, our burst mass, the length of our bar, the distance between string B and A, the mass of our block, and x. So this system is in equilibrium, which means that there's a point, a point that we can choose where the torque will be 0 because the system is in static equilibrium. So we can call that axis P, and we're going to choose it where string B is, because through doing that we can relate it to all of the other masses in the system and how everything fits together. So we start with our torque at P is equivalent to 0 once we determine P. We don't know what it is yet. I just said we're going to pick it at string B. So this is going to be P right here. And that would be equal to the torque in B, because that's also the point for B. So it's at 0 because it's at equilibrium. So what we do to find the torque here is we figure out all of the places where there is force coming from applying torque to this point right here. So we have our tension in string A times the distance, which adds torque, and then, we subtract m1 times gravity, because gravity is pulling this whole bar down all across the length, so we also multiply it by L, and we divide it by 2 because this string, like if this string weren't here supporting it, we would not have to divide it by 2, but because this is like supporting like half of the weight, we don't have to worry about that. And then we subtract our mass 2 times the distance between string B and m2, which is x. And I need to rephrase what I said earlier. The reason that we divide by 2 is actually just because that's where our center of gravity is right in the middle, I believe, which would be L over 2. Okay, so we have this equation now which describes our torque in B at this axis right here. So we know that TB, our torque on B, is equivalent to our torque on P, which is equal to 0. So this entire equation is equal to 0. So we can just rearrange it, and we get that our tension in A is equivalent to our first mass times gravity times our length over twice of our distance plus m2 times g times x over d. So that is how you do number 3, and thank you.